In this work, we present a planning and control framework for non-prehensilely transporting a polygonal object with a wheeled monopedal robot. We take dynamics into account so that inertial forces can be leveraged to achieve more time-optimal solutions than if quasi-static assumptions are made. Material transport is a useful task both in industrial and commercial settings, and we believe that non-prehensile manipulation, which has especially been difficult to implement on robots, is useful when object size, geometry, and surface properties are variable. The loss of force closure makes dynamic motion planning difficult since there are many contact modes, such as sliding and rolling, that the object can undergo. We are interested in regulating the dynamic grasping mode during object transport, which means that the object effectively stays stuck to the end effector. We define this mode as the safe mode, where the object's relative position and pose are fixed relative to the end effector. We start by planning a feasible trajectory for the robot's hip, which will hold the object. Then we plan a full state trajectory for the robot that induces this hip trajectory. Finally, we stabilize the robot about this trajectory using PD joint control. In order to maintain the dynamic grasping mode, we model the frictional line contact as two friction cones, shown in red in the right figure. We can convert the two friction force constraints into one generalized friction cone constraint in wrench space, shown in the figure on the left as the polytope F, which is in the object frame. If the gravito-inertial wrench, which is a function of the system's state and control input, is within this cone, the object will not slip, roll, or lose contact. Note that we convert all wrenches exerted on the object into acceleration space, since we are analyzing this in the object frame. We define four control barrier functions, each of which are used to safely impose the four boundary wall conditions of the generalized friction cone. The barrier functions are defined such that their zero superlevel sets are within the friction cone polytope, and as long as their values stay positive, as shown in the graph on the left, the friction constraints will be satisfied. More importantly, in our optimization, we can impose a maximum decay rate for each barrier function so that the frictional forces do not reach their boundaries too quickly, and we can control how conservative or aggressive our policy will be. Our hip trajectory optimization uses a quadratic objective and nonlinear constraints, which consist of dynamic constraints, barrier function constraints, and workspace constraints. Note that the barrier function hyperparameter gamma is a value between 0 and 1 and is used to make the policy more conservative or more aggressive, respectively. We use a nonlinear SQP in MATLAB to generate hip trajectory solutions, and an example of a solution that keeps the gravito-inertial wrench on the object within the friction polytope is shown on the right. We can compare how varying gamma changes our hip trajectory solution. If gamma is small, as shown in blue, the position of the hip joint takes a more roundabout path towards the goal position, but the gravito-inertial wrench point stays safely away from the friction boundaries. If gamma is large, as shown in red, the trajectory is more direct, but the frictional forces get much closer to their boundaries.
We modeled the dynamics of the robot on the sagittal plane with 2D dynamics. We set up the simulation manually in MATLAB and made a few assumptions to simplify the model. The first is that the robot always rolls without slipping. We're not considering any joint friction, and the object does not alter any robot dynamics. In order for the hip platform to execute the desired hip trajectory, we're using two methods in trajectory optimization. The first we use is direct transcription, which is dividing the whole process into 30 discrete states and try to solve for the full state trajectory of the robot. Once this is done offline, it is fed into the online controller, which is using both feed-forward return from the solver and a PD controller once the robot is out of place. Here are some of the results. The two animations on the first row are the direct animation of the solver output of different trajectories, and the two at the bottom are the corresponding PD controller, which is done online. You can see that in all of these cases, the robot is taking a dynamic move to transport the object into the go state. The second method that we looked into is a Hermite-Simpson direct allocation method, which is dividing the control trajectory into quadratic splines and the state trajectory into cubic splines. We can specify the objective and constraints on the discrete control points. The implementation of this method is largely based on OptimTraj, which is an open source trajectory solver in MATLAB by Matthew Kelly, and here is one of the results. The direct collocation method is in continuous time, so the robot is able to make finer movements compared to discrete time solvers. When using 19 segments, we can still see the cubic splines. When using 30 segments, the robot is able to track the trajectory better, but it's also taking a longer time to finally converge. Finally, we compare the time it takes to deliver the object. With the nominal method, which is moving without tilting the object tray, it takes about 5 seconds, and with the R method, it takes about 3.9 seconds, which is a second faster. Thank you for listening.